Okay, in the last class we derived the finite element formulation based on principle of virtual work. So I introduced the displacement interpolation function and some metrics which relate the strain and displacement. So today I like give you the example for understanding the real procedure of finite element method. Okay. Let's consider simple bar problem. So actually this is in our textbook. It looks like this. The bar consists of two parts, prismatic part and bearing section part. And prismatic part have a constant area, 1 centimeter square, and bearing section part have a changing section depending on the local coordinate. Here we have an area is a function of local coordinate 1 plus whole t square. And at the tip, we have a tip load 100/9 Newton per centimeter square. This is our physical structure. So I like to find the solution, displacement, strain and stress for this simple problem. Okay, so first thing we need to do is discretization. So I need to discretize this physical structure with a finite element. Let's consider only two finite elements. So both have a two node. Okay, this is element 1. This one is element 2. Okay, both have a midline here. So this is node 1, node 1, node 2, node 3. So this finite element discretization, this finite element model have a two element and two node, and each two element and three node total, and each element have a node 2 node. So element 1 have a node 1, node 2. Sorry, here this should be node 2. Element 2 have a node 2 and 3. Okay? And here, let's define the global degree of freedom U1. Let's say this is U1, U2, U3. So at each node, we have a nodal displacement, U1, U2, U3. Okay, then we can define nodal displacement vector U1, U2, U3, right? Okay, then now let's consider element 1. Element 1, let's say element 1 has a displacement. This is a displacement of element 1. Displacement of element 1. So U1, that U, small u, can represent all the displacement in the middle element, in the element. Okay, so this element have a nodal displacement U1 and U2, right? So using this U1 and U2, we can interpolate displacement of U1, right? So let's define the linear coordinate system. So local coordinate from x start from here. Then it become 1 minus x 100 u1 plus x 100 u2, right? Let's put x equals 0. Let's put x equals 0 here. What happened? X equals 0. This becomes 0. This becomes 0. So we have only u1, right? So this is correct. How about x equals 100? If x equals 100, so 1 minus 1, this becomes 0. 100 over 100. So we have u2, right? So this is a correct interpolation function. So in matrix form, 1 minus x over 100, 0. u1, u2, u3. Even we have u3 in global freedom vector, nodal displacement vector, here we have a 0 component, right? So this become h, h1. So h1 is a displacement interpolation function for element 1. And let's calculate strain for element 1. Okay, this can be very simply calculated. U1, right? Then it becomes directly minus 100, 100, 0, U1, U2, U3. And this matrix become B matrix, B1. So now you know how to find the H matrix, displacement interpolation matrix, and B matrix, strain interpolation matrix, right? We can do exactly same job for element 2, okay? Then U2 become, let's define the another local coordinate system from here, x. Then 1 minus x over 80 u2, right? Plus x over 80 u3 equal 0, 80, U1, U2, U3. This is a H2. How about the B2? Let's say B2, EXX2 equal, B2 is very simple, right? 0, 1, minus 80, 80. And here, U1, U2, U3. Right? So we already calculate the B matrix for element 1 and element 2. Okay, then we can calculate the K. K1 equal 1, area 1, okay, and E, Young's modulus E. This is one-dimensional problem. So the material law becomes just one value, 0 to 100, minus 100, 1, 0, 0, dx. This is area. Okay, so area is constant, and here integration is about the length. So actually, all of this means volume integration, right? Same. So because the area is constant, the volume integration just become line integration. Similarly, K 2 E same 0, 80. In this case, for second element, the area, cross-sectional area of bar is changing. So I need to put here the effect of area. This is area, right? Square of area. dx. Right. So we need to do some calculation. Okay, the total stiffness matrix equals just sum of both 1, K2. Then we can have E over, yeah, okay, so let's say something just right. Let's calculate the also external force. So at this point, external force is applied was 100 Newton per 9 square centimeters square. So at this point, the area is, yeah, put the 80 here. Then we can find out the area is 9. Oh, sorry, there is something wrong here. Area, this should be plus, okay. Not minus. Okay, right. So if I integration of the Stropies supposed to mean the distraction multiplied by area. So it becomes just 0, 0, 100 Newton. This is a external force vector. So finally, we have a system Ku equal R. So E 240 0 U1, U2, U3 0, 0, 100. This is a final linear equation in matrix form. Okay. Okay. So now we can calculate U1, U2, U3, right? We missed something, very important thing. What's that? We calculated steepness matrix, right? And we calculated the load vector. But we didn't consider one very important thing. What's that? 정호? Boundary condition. We didn't consider boundary condition. So what's the boundary condition? Boundary condition. Displacement boundary. U1 equal 0, right? Okay, so because U1 equal 0, virtual displacement U1 equals 0, 2, right? So here U1 equals 0. So it means we don't need to use the first equation here. Okay? U1 equals 0. Okay, then we have a matrix. This is not a square matrix. This condition gives us deleting the column. So this equation originally from U transpose K U, right? You remember? So we have a transpose here. This condition should be imposed by deleting this line. So finally we have a system E only this part U2, U3 0, 100. Right, now we can solve this equation. Okay, let's look at the first equation here. In this equation, displacement boundary condition is not imposed, right? So it means rigid body motion in x direction is allowed. Okay? And it means this steepness matrix is singular. We cannot solve. So this steepness matrix doesn't have an inverse matrix. So if you try to solve, you cannot solve. But once we apply the boundary condition, so just simply deleting these two lines, we can have this equation, and this steepness matrix is not singular. This matrix have a inverse matrix, so we can solve. This procedure is very important, okay? Okay, then we can solve, we can find out U1, U2. U1 equals 0, right? So U1, U2, U3 equal 0. U1 is 0 due to the boundary condition. And if I solve that 2 by 2 linear system, U2 and U3 are calculated. So E over 1 okay, something like this. So now we know displacement, nodal displacement. So we can calculate the strain, right? By using the B matrix and also stress. So for example, I'm going to give the solution E1, E2, okay, sigma 1, 100, sigma, okay, x 2, something like that. So problem I gave you looks very simple, but it has a lot of information. So for the solution procedure for general case, for example, 2D or 3D solid problem and plate and shell problem and beam problem, the procedure are exactly same. Only difference is that how to approximate the displacement field, okay, for the first procedure. Okay, that's only difference. And there are some assumptions are different, but basic procedure are exactly same. Okay, so you can think like this. Finite element method is based on principal virtual work. And it has a very well established procedure. So finite element procedure have a standard procedure to use the principal virtual work to solve solid and structural problem. So in the lecture, in this first semester, I'm going to teach on finite element procedure. Okay? Okay, so any question? Yeah, let's look at here the stiffness matrix. One very important feature is symmetric, right? Now let me talk about why this matrix is symmetric and why this matrix should be symmetric. Okay? So in structural mechanics, the stiffness matrix should be symmetric. That is reciprocity theorem. Okay. Let's consider we have a structural body here, and this is fixed. And this body have a two load, F1, okay? And this is applied, the point 1. And here, F2 is applied to point 2, right? Solution for this case, this have two load case, right? Can be calculated by solution about the F1 plus solution about F2. Oh, sorry. F2. F2. If I first calculate the solution for single load case F1 and then calculate the solution for single load case of F2, if I superimpose the solution, we can calculate the solution for two load case, right? What's this? This is a principle of superposition. Superposition, right? This is very well known. We already talked about this before. So, in other words, we can think about also two cases. First, we applied F1. Okay, so let's consider two cases. First, we applied F1. So we are considering static analysis, the static load applying procedure. So we applying the load very slowly, right? Very slowly. Okay, from 0 to F1. Okay? Then let's apply the force F2 very slowly. Okay, from 0 to F2. So, loading sequence. This static. That's very slow loading mean static loading. From F1 first. And F2. Even I sequentially apply the F1, F2, the result is exactly the same to we apply the both load together statically, very slowly, right? I can load the F1, F2 together from 0 to F1, F2, right? Very slowly. But final deformation will be exactly the same. And all the energy stored in the structure should be same, right? Okay, so let's consider first case. So here we have our original deformation, and I'm going to apply F1 at point 1. Okay, then this will deform somehow like this, okay? And point 1 will move. This is displacement at point 1. This is U1. U1. Then external work. Let's calculate the external work. equal 1 over 2 F1 U1, right? Because we apply the load F1 0 to F1. This is time t, right? This is the external work applied by F1, right? And then now I like to apply F2 here. This is position F2. F2. Then this is a deformed situation. Okay. So this part will move. Let's say this is U2 plus 1 over 2 F2 U2. Okay. Is that all the external force? External work done by external force? There's something missing. So that is this part. F1, when I applied F2, F1 already applied, right? So this part also move. Let's say this is a U21. So during the second loading, F1 will work also. So but F1 is constant during the second loading. So F1 U21. This is a total external work. Okay, applied to this structure, and all of this work will be stored in the structural system, right? Is it right? And now let's consider another another static loading sequence from F2, F1, right? Then external work equal. First, I'm going to apply F2. So equation during because of the F2, we have external work F2 U2 plus I'm going to apply F1 1 over 2 F1 U1, right? Plus F2 will work F2 U21. So here U21 and here here U12. U12. U21 is a displacement at 2 due to load F1, right? And this is a displacement at this is a displacement at 1. This displacement 2 due to load F1. So both are different meaning. So if I consider both loading case, the external work should be same, right? So it means finally we can conclude that F1 U21 equal F2 U12. This is Betti's reciprocity theorem. Okay. So and here and similar thing is that Maxwell's reciprocity theorem. Maxwell. In his case, he applied F1 equal 1, F2 equal 1. So he applied the unit F1, F2. And U21 equal U12. This is Maxwell's result. Same thing. Only difference is that the force is unit or not. So it means, physically mean, displacement at place 1 due to load F2 is exactly same to the displacement at position 2 due to F1, load F1, right? Little complicated, right? So displacement, so during this deformation here, this is a displacement at position 1. This is U21. And here, let's say, second. This is, let's say, here displacement from here, let's say here. It's a bit complicated. U12. So when loading 1 is applied, we can measure the displacement at position 2. That's U12. When we load the F2, the displacement at position 1 is U21. Both displacement is same. Okay, this is Maxwell's theorem. From this very important physical investigation, we can find property of stiffness. Of stiffness matrix. Okay. So K U equal R, right? Or we can write down K inverse R equal U, right? What's the name of K inverse? This is flexibility matrix. matrix, right? And let's consider flexibility here over there. It has F11, F12, Fn1, F21, F22, something like that, Fnn. This is a flexibility matrix. Let's say this is a K inverse. And here, R1, R2, Rn. And here, U1, U2, Un. Right? Okay, now let's look at this system very carefully. I am going to apply the load F1 equal 1 and others is 0. 0, all the 0. Okay? Then let's see the U2. Let's calculate U2. So when R1 equal 1 unit and other R equal 0, U2 become F12, right? This means this F12 equal is a displacement, right? At position corresponding to U2, right? So this is the same to the here U12, right? This is U12, same. Over there, that this is a U12, right? In Maxwell reciprocity, F12 is equal to U12. Also, second case, when R2 equal 1 and other R I is equal 0, U1 equal F21. And this become U12. So this means F12 equal F21, right? So for other load and displacement, we can do exactly the same job. Then we can find out this flexibility matrix is symmetric, right? It means flexibility matrix is symmetric. So inverse of flexibility matrix is a stiffness. Stiffness matrix is symmetric too, right? So very important result is K Ij equal, so K transpose equal K, symmetric. Stiffness matrix is symmetric. That's the first property we should remember for the stiffness matrix. This is first property, let's say 1. Second property 2. Let's consider our system KU equal R and external work. How can I calculate the external work? This is just 1 over 2 U T F, right? If I dot product UTR, the external force and this displacement, we can calculate the external work, right? And again, this becomes 1 over 2 U T K U. Yeah. We can put this into here R, right? This gives us external work. And also that gives us the work stored in the structural system. This is same. Strain energy. Right? So, energy should be always positive, right? So, this should be bigger than 0. So, this means when displacement is not 0, UTK U should bigger than 0 for all U. What's the name of this property of stiffness K, matrix K? It means positive, definite. So, this is a definition of positive definite. So, stiffness matrix is symmetric and positive definite. Okay?